So thank you for the introduction. So first, let me thank the organizers for the kind invitation. It's been a really fantastic program so far, and it's been great to be able to participate. So I'm going to talk about a few things today, but the main results will be joint work with Christopher Warholm, who's at Norwegian University of Science and Technology, and Erik Valen, who's probably well known to this crowd, who's at Lund. And so the main topic is stability of traveling waterways with a point vortex. Okay. All right, so we're sort of far into the program, so I can dispense with a lot of the background, but the basic setup is the following. So I want to look at traveling water waves, so steady water waves, and they'll be in 2 dimensions, so they're living in R2. I don't want to do time at all, well, at least for the most part, so I'm going to just immediately shift to a moving reference frame, which means to me that I am looking at this at a frame which is moving with speed c, a constant to the right, and at that point the wave occupies some time-independent region omega. So the variables are x, so x has 2 components, x1 and x2, and omega lies above minus d, the vertical component coordinate lies above minus d, and below some eta of x1, which is the free surface profile, which is a priori unknown. So here, for the most part, I'm going to be talking about infinite depth, which means that d will just be plus infinity, but briefly I'll talk about finite depth, so I want to be clear what that actually means. Okay? So, all right, so here's the setup. These waves are governed by, at least as far as I'm concerned, are governed by the steady incompressible Euler problem. So we have the momentum equation in the steady form. Here the v is the velocity field, which is, remember, 2-dimensional. P is the pressure, so it's scalar. G is the gravitational constant of acceleration, which will be positive, so we always have gravity in this setup. We have divergence-free conditions, so it's incompressible. On the boundary, we have the usual kinematic conditions, so here capital N is the outward unit normal, so this is quite standard. And then we have the dynamic boundary condition. So the pressure is proportional to the signed curvature, which is the kappa is the curvature, and tau is the proportionality constant. For most of them, I'm going to talk about tau will be positive. So these are so-called capillary-gravity waves. And so again, the surface is given by the graph of some unknown function. Here I drew d, it doesn't look like infinity, but it's going to basically be infinity here. All right, so the vorticity, as we all know, is a scalar, or usually identified with a scalar when you're doing 2-dimensional problems, and it has, with my convention, is this exact quantity. So I call it, historically, and even currently, I would say the vast majority of the work in water waves is under the assumption that you have irrotational flow. So the omega just vanishes identically. This is justified in many physical regimes. It's propagated by Eulerian dynamics, so it's a perfectly reasonable thing to do many times. And maybe more appealing for mathematicians is that it enables a lot of very powerful machinery. And so because you immediately get to write the velocity field as the gradient of some potential, which is harmonic, and then more or less the difficulty only remains to figure out where the boundary is. So there's many different techniques for pushing the problem to the boundary or compactifying it that make it more tractable. Okay, so on the other hand, rotational waves do occur in nature, and for many different reasons. Wind forcing, I think, and more boundary layer effects on the bed, which we've seen. Density variation, which is my personal favorite. But however you get it, you do see your vorticity in nature, and mathematically it's an interesting thing to look at. So this is something that many people in this room actually have had a hand in advancing, and progress has been much more recent. But okay, over the last, so Constantine and Strauss made this very influential work in 2004, and over the last decade or more than a decade now, I guess, we've, as a community, been really doing a lot of work in this area, and we now have a lot of existence results and other types of results for rotational waves. So this is, I'm not going to even go, the bibliography here would take up multiple slides, so I'm not going to bother with it, but we can do gravity waves, stratify waves, infinite depth, finite depth, critical layers, capillary-gravity waves, and many other regimes of rotational waves. Okay, so despite all that, literature. This is still by far the less explored of those 2 regimes. Okay, so I just want to point out though that all of this work much of this work that's we've been doing for the past decade has the common feature that actually, even when you do have vorticity, I mean, when you do have vorticity, it's not compactly supported. Actually, it's not even localized in any sense. And so this is I mean, I don't know if this is a conscious decision on anyone's part, but I mean, I would say it's more like a consequence of the way in which we typically construct these waves, right? So you start off, as we said actually in several of the talks already, with a shear flow, a family of shear flows, and you do a perturbation. So, but shear flows, you know, the vorticity is a constant along the streamlines. The streamlines go out to plus and minus infinity. So no matter what, you start off with vorticity at infinity or no vorticity at all, and this is usually continues at least in local bifurcation. So if you're doing this kind of a construction, it's very hard to see waves where you have where you don't have a vorticity at infinity. Okay. So just to summarize, you know, there's a vast body of work, still growing on irrotational flows. There's a large number of works on rotational problems where you have actually no vanishing of the vorticity at infinity whatsoever. But I mean, so there's an important, I would argue, there's an important middle ground between the two, where you have traveling waves where there is vorticity, but the vorticity is some way localized, right? So it doesn't, at least let's say it vanishes at infinity, it could be compactly supported, or any number of other types of problems. Okay, so this is a physically relevant scenario to look at. So I've been looking, I've been doing this now for a couple of years over several different projects with many different collaborators. So this talk, I guess, is really going to be, well, I'll talk a little bit about the existence theory as far as I need. So for specifically resistance theory for traveling waves with point vortices and vortex patches, and some ongoing work on stationary waves with exponentially localized vorticity. But that's sort of the preamble. I mean, the majority of the work is going to be discussing stability theory, so particularly stability theory for these point vortex traveling waves. And so this is the work with Eric Verlaine and Christopher Varholm. Okay. So let's start off with point vortices, existence. So if you want to look at waves with localized vorticity and you don't want to start off from shear flows, you need to start with something. And sort of the most cartoonish way you can get, fly is very well positioned. I mean, the most extreme way you can get localized vorticity is just to say the vorticity is a delta function, right? So this is what's called a point vortex. You look for solutions where the omega is just epsilon times delta x bar. So epsilon is the mass, which is the vortex strength, and x bar is the center of the vortex, which should be somewhere in the flow. Okay, and so this has been studied extensively for planar flows, but we were interested in putting this inside of a wave. Okay. So if you anticipate having the velocity field or the vorticity have this form, a natural way to proceed is to make a splitting of the velocity field that sort of exploits the fact that you know what the rotational part is very explicitly. So what we do is we write the velocity is the gradient of a harmonic function, the potential for the, say, irrotational part of the flow, and then an extra term which is going to be the gradient perp of some gamma, right? So the gamma will be a divergence-free, or so this will be a divergence-free vector field, and epsilon is going to be the vortex strength. So we've normalized it a bit. You can always do this, of course, and you see very quickly that if you want to have this ansatz, just take the divergence of the equation, and then that kills the phi, and so you see that the Laplacian of gamma has to be the delta function if that's take the curl of this, kills the phi, and then you get immediately that so that what should gamma be? Well, it has to be the Newtonian potential up to a harmonic function, and and you do want to have that freedom to choose the harmonic function, because remember that we're working in R2. And we'd like to have waves that are finite energy, so energy, L2 energy, that is. And you can see that finite L2 energy means that gamma should be in H1 dot, the homogeneous sublow space, and you just miss that if you have, the Newtonian potential just misses that in R2. So you just add something, a harmonic function that gives you enough cancellation at infinity to get integrability, or square integrability. So this is, you can kind of think about it a little bit poetically as adding a phantom vortex that is exactly the opposite strength outside of omega. All right, so if you do that, and imagine that we have a point vortex in the flow, and I want to think about what's going on at the surface. Well, as long as the surface and the point vortex are positively separated, then I can find some strip around the surface and actually write the velocity as a gradient there. And I mean, I can do that in a way which respects this previous splitting, by just saying, okay, it's the gradient of phi plus epsilon gradient of psi. And what is psi? It's the difference between two functions, psi1 and psi2, which have this sort of unpleasant form. But psi1 is really just the harmonic conjugate of the Newtonian potential in R2, right? So this is coming from the gamma, the Newtonian potential. And psi2 is basically the same thing, but you have a plus sign, right? So this is like the the harmonic conjugate of the phantom point vortex. And you can see that these are arranged exactly so that you get some cancellation at infinity, and it gives you everything is, makes sure that everything is an H1 dot for the velocity, or for the potential. Okay, so why is this useful? Well, now we go back and look at the kinetic condition again. So this is it when you actually have this graph geometry. You can write it out explicitly. And I've just replaced the velocity field with the splitting, so I can write it as the gradient. And likewise for the Bernoulli condition, we have something that looks like this, right? So this is the standard form you would see if you just did the rotational flow, except everywhere I used to have just phi, I now have this epsilon psi. But psi is explicit, right? I mean, as long as I know where the point vortex is, and it's also perturbative, because I'm thinking about epsilon as being small. So this is a pretty nice set of equations to work with, and we understand it pretty well. Particularly, I mean, we know that there's a very powerful, Hamiltonian formulation of this due to Zakharov and further by Craig and Sulem, which you can reformulate everything basically on the boundary. And so how do you do that? Well, you just take little phi to be the restriction of capital Phi to the boundary, so you compose it with eta, and then tangential derivatives of capital Phi become, can give you derivatives like an x1 of little phi, and you can recover normal derivatives using Dirichlet-Neumann operators. Right? So the non-normalized Dirichlet-Neumann operators, so we know. Okay, so this is, I think we've seen actually this in several talks. It's not very revelatory, but the point is, of course, that you can still do this even though you have vorticity, and all that happens is that you get a bunch of these sort of forcing terms, right, with these epsilons on them, and you have to, but you can approach it as you would if you were, doing, say, time-dependent theory for dispersive PDEs or whatever whatever your favorite application of this sort of technology. So you get these two equations which really gives you almost all of the motion of the boundary and also the pterodynamics. Okay, so that doesn't completely close the system though, because you need to know something about what's happening at the point vortex itself. And I've sort of glossed over one important detail, which is that, I mean, technically speaking, these aren't actually weak solutions of the Euler equations, right? So when you have a point vortex, I mean, you think about the velocity, so the derivative of the velocity is like a delta function, so the velocity can have jump discontinuities, and so there isn't really an interpretation for the nonlinear combinations of the vorticity or the velocity and its derivatives that you get in the advection term, right? So you can't just write, this is not a weak distributional solution of the Euler equations. You have to sort of make an even weaker definition of what Euler is to accommodate this class of solutions. And the way in which this is done typically is you imagine taking waves where you have the vorticity supported on a disk and then shrinking that disk to 0. And what you find is there's an effective equation for the motion of the center of the disk. And basically it says that the point vortex should be advected by the flow, but the velocity field, but not the entire velocity field, because it shouldn't be advecting itself. So you take the velocity, you subtract the contribution of the point vortex to the velocity field, and that's what moves the point vortex. Okay, so you take that as your governing equations, you write that in for steady waves, and you use the splitting of the velocity field that we've introduced, and you get this basic relationship. So at the point vortex, the wave speed has to agree with, so this is the potential for the irrotational part of the flow, and then you have, this is the phantom vortex, right? So it's getting, it does see the phantom vortex in the air. Okay. So for all this discussion, I'm just going to fix the vertical position, actually, and the horizontal position, so that's at, say, 0 minus a, where a is an altitude. I'll think of it as a parameter, but these waves are going to be even around the x1 axis. So 0 is a good choice. Okay, so then you want to make an existence theorem, you have to state a function.
That last line, does it mean that the vortex is on the surface?
No.
What does this mean? A is the amplitude?
So the vortex is, no, so the surface is a perturbation of 0, or it doesn't look like that, and this is,
sorry.
That's fine. It's good to have it on the board anyway. Okay, it's inside.
So where's the phantom vortex then?
Phantom vortex is reflected across the line x2 equals 0, so it's sitting there. So is it 0 plus a, I guess. These are small amplitude waves, so it doesn't ever see the surface.
Ah, yes, okay.
Yeah,
Sure. That's what caught me when you said.
Yeah. So of course, yeah, you have to be.
So so local for the vortex, it's treated as flat, and
Yes.
therefore it's right above. Okay,
Right.
sure.
Okay. Actually, that's a very bad picture. I'll give you a better one in a second.
It's not small.
Sorry. Okay, so all right, so this is the function space setting. So we're doing everything in Sobolev spaces. You need homogeneous Sobolev spaces for the the stream function, or the velocity potential for the irrotational part restricted to the free surface, phi, and this is eta. The subscript e and o are for even and odd symmetry. Okay. So these have finite energy is the point. Okay. And they're sufficiently regular. The smoothness isn't really that important. Okay, so the first theorem is which was done with Joel Shatah and Chengqun Zhang, and then sort of re-examined a bit with Eric and Verlaine and Christopher Verholm. It's just that you can construct these waves, right? So choose whatever sort of initial altitude you want. There's some parameter, maximum vortex strength you can get, and a C1 solution of solutions that are parameterized by the vortex strength and by the altitude. So you can slide it up and down a limited amount, and you can turn the vorticity on or off. So this is a very funny theorem in some sense, because this is we're bifurcating from 0, right? You usually don't do this in water waves, but so these things are slow-moving, small amplitude, small vorticity, small in every way, but they're there, right? So and you actually get them, right? And they give you everything in the neighborhood of 0 in this function space. And so this is actually a very easy argument, surprisingly. When you write everything down, you can just use implicit function theorem, nothing fancy at all. This is partially because we have this surface tension, but anyway, so you do it, and you can get very nice formulas just from implicit differentiation for what these things look like. So this is the graph I have here. So this is very bad scale, but okay, they look like our capillary gravity waves of depression that you would imagine. And you have their leading order term for phi, eta, phi, and c. Okay. And this is big O in this Sobolev space, right? So actually, I mean, we went back in other work with Ming Chen and Miles Wheeler and redid this theory and weighted Helder spaces, and you can show that these are so algebraically decaying. So they, with some weight, which is like, that's the Japanese bracket. So they behave like x squared if you're going to infinity in the horizontal direction, sorry, they decay like 1 over x squared if you go to infinity in the horizontal direction, and 1 over x if you go to infinity in the
motivation to do it in the Hilbert space?
The motivation to, I mean, so the main contribution in this paper is to actually to determine the leading order form of the waves at infinity, asymptotically. And so we do this using a method that actually Miles introduced looking at the irrotational theory, which presupposes that you have algebraic decay estimates of this form. So before we could actually apply it, we had to go back and redo all the existence theory to put it in this framework. And actually, this was surprisingly difficult to do. Maybe other people have more expertise, but there's a long road from this kind of a statement to this kind of a statement. And these are optimal, by the way, because they come from the decay rates you get from the Green's function for the Laplacian in the half plane. And so I don't think you can do better than that. I can't. Okay, so as I said, existence theory isn't the main focus for today, but I do want to mention some other things that have done in this area. So there's much earlier studies of steady gravity waves with a point vortex in finite depth by Krikharov and 2 papers by Filipov. And also, if you have capillary gravity waves with 1 or more point vortices, this was in finite depth, was done recently by Verholm. We actually have a global bifurcation argument for the periodic case for capillary gravity waves with point vortex. So global bifurcation in the sense that you can put it into the usual machinery and you get the sort of many alternatives that we don't have that for solitary waves yet. But, okay, that was done with in the original paper with Joel and Chengqun. There's another sort of related work which is now not talking about point vortices anymore, but just about compactly supported vorticity. So Adrian has this very interesting paper where you just have in 2D you have a sea which is completely at rest except for one region where you have vorticity, and because everything is at rest, I mean everything's stationary, you can put whatever bed you want, so it doesn't have to be it can be a beach. And then sort of in the same vein, we also, in the initial paper on the existence theory, we looked at small amplitude traveling capillary gravity waves with vortex patch. And so when I say patch here, I mean it maybe not in the most common sense. So the vorticity doesn't have to be a characteristic function. It's basically you choose the vorticity function of any kind you want in a generic class, and you can create a patch of vorticity which has that vorticity distribution, and then which lies inside a water wave, a capillary gravity wave. So this is much harder than the point vortex case, actually, but we haven't done much with it since then. And then also, so in kind of ongoing work with Eric Folland and Mats Ernström and Chengxin Zheng, we've been looking at small amplitude, stationary actually, capillary gravity waves in finite depth where you have exponentially localized vorticity. So they're not compactly supported anymore, but they're allowed to kind of smear out, and you get exponential localization. So this is hopefully something we'll be able to report on more in the near future. Okay, so that's it for existence, and talk about stability. So the point vortex waves. Okay. All right, so the main machinery we do this with is actually sort of a relaxed version of this classical work of Grillakis, Shatah, and Strauss, which is a means of getting stability results, or orbital stability for families of solutions of abstract Hamiltonian systems. Okay, so the first thing you need to do, if that's your intention, is to show that this actually is a Hamiltonian system. So this is reasonable to expect in some sense, because if you're in the plane, this is a very famously known to be Hamiltonian. If you don't have the point vortex at all, then of course it's Hamiltonian. So you might hope that they don't destroy each other by putting the point orders in the wave. And there actually is, a very nice paper, a formal paper, but a nice one by Ruhi and Wright, where they do make a derivation of a Hamiltonian formulation for this problem. They do it in different variables than we did with the existence theory, so we had to kind of go back and do it quite differently. But okay, so this is a very intimidating slide, but let me try and parse it. So the energy, so it depends on eta, phi, and x bar. Those are our variables, and epsilon. You can break it into the kinetic energy k and the potential energy v. K has this sort of horrible form. V is this form. Let me actually just go to the next slide. So hopefully you can see this. So the things that are highlighted are the ones that you expect to see in a standard Hamiltonian formulation for water waves. So everything else you see has an epsilon in it, and these are the effects of the vorticity, or the point vortex. So you get sort of an interaction term between the irrotational part and the rotational part, and then you have some sort of nonlinear, sort of quadratic terms where you have the rotational part interacting with itself. And then you have this funny term here, which is a little harder to explain, but needs to be there. And so the potential energy act doesn't see the vorticity at all, which is quite nice. And then there's a momentum, which is given by the usual thing, but there's something from the motion of the point vortex itself contributes to the momentum, and there's of course, some contribution of on the surface as well. Okay, so that's the energy, and you can indeed show that this gives you a Hamiltonian system. It's a very unpleasant Hamiltonian system, and it has this sort of form. So the variable u now is eta phi x bar, and you have this very complicated-looking skew symmetric operator, capital J, which depends on both u and epsilon in sort of complicated ways. And but nonetheless, it is a Hamiltonian.
How do you know that it satisfies, in this case, Jacobi's identity? Because it's not the J's with the various sub-indices. They depend, by the look of it, on the variables, right?
That's right. Yeah.
So that means that it now Jacobi identity is non-trivial. So how do you, skew symmetry is not enough. So how do you need skew symmetry, but it's not enough. So how did you had to do the laborious job of proving Jacobi identity?
Well, okay, so maybe better to say that it fits the description. It is a Hamiltonian in the sense, an abstract Hamiltonian in the sense that one can build a framework analogous to what is done in GSS that will work for this, and has enough structure to do that.
What's GSS?
Grillakis, Shatah, Strauss. So I'll go through all the properties that this has in a moment. But of course, this is not. It's an infinite dimensional Hamiltonian system, so I don't claim that it necessarily has every piece of structure that you would hope for. We can verify all of that. We just did enough to get the stability
maybe it
theory.
does. I just
No, it may or may not. Right? But basically our concern was whether or not we could apply the stability theory, and so we only verified the components of the abstract theory that we needed.
Oh, that would hint, if that works, that there is.
Yeah, hopefully. Right.
Yeah, but it can be quite laboursome if it's non-canonical, which is what it is.
Yeah, absolutely.
And then you have to do the cumbersome job, or use a smart trick somehow. And
I'm not that smart, unfortunately. It was
I think you are, but I just.
No. This has been we've been struggling with this for quite a long time, and I'm sure there are many struggles down the road as well. But.
The third and fourth components are the components of x bar.
Yeah, so this is the x. Yeah, that's right.
Could you just remind me, what's the equation for x bar? What does it look like?
It's just that, let me see if I...
The time derivative of x
x dot bar, time derivative of x bar is advected by the irrotational part of the velocity field. So you just take the you take little phi, which is the restriction of the velocity potential of the surface. You take its harmonic extension, take its horizontal derivative to get the horizontal velocity, and then you add in the point vortex.
Oh.
So that's why you're getting. I mean, this part is just like what you would see for basically a point vortex in the plane. That's nice. What's unpleasant are these things where you're having interactions between the point vortex and the various other components.
So what you see, if you take the J0, which are the coupling terms, that the respective pieces are canonical, and therefore a normal, the vortex piece and the wave piece are canonical Hamiltonian systems in their own right. But then when you couple them, it's the question. Now what we also know is that the starting system is Hamiltonian before you put in the vortex. So if you carefully go through that route, you might by construction have preserved it, but you have to very carefully check. So it may well be in there. If you did that carefully enough, it's kind of a guarantee by construction because your starting point was Hamiltonian. So your starting bracket satisfied Jacobi identity, and when you do your approximations and you didn't do anything peculiar, which is non-trivial, then you're safe.
Well, this is maybe we should talk about that later. I really appreciate the guidance. Okay, so but let me try not to go over my time. Okay, so then you can show that actually these traveling waves are the critical points of the augmented Hamiltonian, right? So you take the energy, subtract off c times the momentum, and so you can effectively think of steady waves as minimizers of this energy subject to fixed momentum, which is of course a very productive point of view in many aspects, but also one which has been used a lot in waterways. So the wave speed basically occurs as a Lagrange multiplier, and so you do have to verify that, but it is indeed true. Okay, so then the idea abstractly is to try and use this Grillakis-Shatah Strauss method, and let me just give you kind of a cartoon sketch of what that entails to see how well that fits our problem and what we need to do. So let's step back and look at just a general problem now, not the one we were looking at before, and say we have a Hamiltonian system that has a more standard structure. So du dt is some j d e of u. So u is taking some values in some energy space, capital X. This is the Cauchy problem. We'll assume is globally well posed. Sorry, it's not. X is a Hilbert space. J here is a skew symmetric operator from X star, the dual space of X to X, and surjective. So all of those are quite important. And we assume that there's some sort of a symmetry. So the simplest one is a translation symmetry, and that symmetry generates then a conserved quantity, the p again. And we suppose that we are given a family of traveling waves, so capital U sub c, so indexed by the wave speed, that are critical points of the augmented Hamiltonian, which is defined as before, and that we have a very particular structure for the spectrum of the second derivative of the augmented Hamiltonian. So it has a single negative eigenvalue that's simple, 0, which is basically generated by this translation symmetry, and the rest of the spectrum is strictly positive and separated away from 0. So if you happen to find yourself in that situation, the main idea from this paper is that there's this quantity, a scalar quantity called the moment of instability, which is just You take a given wave speed and you evaluate the augmented Hamiltonian for that wave speed along your family. And if D is convex at C, then UC is orbitally stable. And if it's concave, then UC is orbitally unstable. So this is a really powerful statement. You can just check a scalar function and take two derivatives of it and see whether or not you have stability or instability. And if you happen to be in the exact situation where it describes, it's a great tool. So unfortunately, the problem we're looking at doesn't fit into that for a number of reasons, many of which we actually already discussed. So Rj is state dependent, right? So it depends on both U and epsilon, so that doesn't work at all. Even for fixed vorticity, so if you fix the vorticity, you still have this U dependence, which gives you this non-flat symplectic structure. Rj is actually not surjective either, which is a pretty big problem. And there is no global well-posedness theory. Actually, there's no even local well-posedness theory for this problem, but you wouldn't even expect to get global well-posedness in an easy way, right? And certainly, you wouldn't be able to get it at the level of the energy, right? If we're looking at L2-based energy spaces or even HS spaces, I mean, you're not going to, it's too greedy to expect that you're going to be able to prove a theorem that gives you global well-posedness in L2 or something, or sorry, at the energy space. So these are major obstructions, and they're actually not, I mean, they're not specific to our problem. They're pretty common in lots of water wave applications. So just, I mean, the most famous one, let's say, is KdV. J is dx, which isn't surjective in most.
You said E and P are defined if you assume more regularity.
Yes.
With respect to what? More regularity with respect
well,
to...
E and P use Dirichlet-Neumann operators. So you need a certain amount of regularity for the free surface to have a well-defined Dirichlet-Neumann operator, right? And you need more than you can being just in the energy space. Yeah, so, right.
More than the energy space.
Yeah, for sure, quite a bit. All right, so this is KdV is a common example where you have a J that doesn't work immediately in this theory. There's other ones. So Benjamin has this an interesting Hamiltonian formulation for internal waves where you have the density, rho is one of the variables, and also this so-called vorticity-like quantity, which is given as this sort of divergence of the rho times the gradient of C, where C is the stream function. And you get, if you do that, you can, it's a very nice paper, actually. I mean, it's in a very nice paper, but you have a formulation and you get J, which has a kind of a strange form here. But so that clearly you're not going to have, well, this is both state dependent and not surjective, I believe. Okay, so then, as I said, so a mismatch between the energy spaces and the space where you can prove well-posedness is typical anytime you have to do higher order energy match methods or many of these techniques that you need from nonlinear PD to conquer very difficult problems. So this is something we grapple with frequently. Okay, so that in mind, we basically went back and tried to take the ideas from Grillakis, Shatah, Strauss and relax the assumptions so that they would accommodate the problem we were looking at. And as we did it, we made an effort to do it in a systematic way so that you can apply it to many problems in different classes. So this is a new abstract version of the Grillakis, Shatah, Strauss theory, which is applicable to problems in this form. So it's very difficult to give it in the full abstract sense, so I'm going to state the main simplified version of the abstract theorem and then give an example of the point vortex, which is a little easier to understand. Okay, so in place of the energy space that you usually see, I want to have a gradation of spaces. So there's X, which is the energy space, or the space we'll do our spectral theory. Inside of X is W. Maybe I'll say these are. So W stands for well-posedness space. This is where you can prove your well-posedness theory and have everything makes sense. And V is an additional space which is even of smoother functions than W, so they call it the very smooth space. And I'll come back to what that means. So in the point vortex case, X was this quantity here, so you see that this is actually exactly the energy space for the problem, and you have a natural inner product for it. Okay, so what is the well-posedness space? Well, we don't have one for this problem, but in general, the idea is you should think of W as being one where it's fair to assume that the Cauchy problem is locally well-posed for initial data in some open set sitting inside W. And for us, okay, so W we presume has something of this form. This is what you'd see if you didn't have the point vortex, and it seems reasonable that that would be true. Otherwise, so that's greater than 3/2, say. But so we take that as an assumption. But okay, so what is O in this case? Well, you need, for this to make sense, I guess as we pointed out, you need to make sure the point vortex doesn't hit the surface for one thing, or that the surface doesn't hit the, well, okay, this is infinite depth, so. Okay, many other things can happen, self-intersection, blow up. So we need to, this only makes sense while we're in some set where we have positive separation of the point vortex from the free surface. Okay, that's our O. So V is this very smooth space, and the point for that is that, okay, you need to, X is where you're going to get everything that you do with your spectral theory that, Grillakis, Shatah, Strauss have sort of done. This tells you what's going on at the energy space. You want to control something in a much higher regulator space, the well-opposed in this space. So a natural way to try and go about doing that is to have uniform control in an even smoother space, right? So that's the very smooth space, and you want to be able to interpolate between the very smooth space and the energy space, right? So that's this basic assumption. So you should be able to control, say, a cubic nonlinearity in the well-posedness norm in terms of a quadratic one in X and a linear one in V. Right? So you can take that, in the point vortex problem, this will work, and this is just Gagliardo-Nirenberg interpolation inequality. Right? It's not very deep, but you need something of this form. Okay, so X star is the dual of X. I mean, in I will be the natural isomorphism between X and its dual space. So you have this pairing that's given by the inner product. For the point vortex, we have very nice form for I, and let's see, ID here is the 2D identity matrix. Okay, so then the abstract. So we consider the abstract Hamiltonian system of this general form. So du dt j of u. So it depends on u potentially dE of u. The energy is going to be smooth. So C2 now it's restricted to this open set, right? So in the well-posedness space. And whenever you have U and O, we have that J of U is defined on its domain of definition is densely defined closed-linear operator with a dense range. Right? So it doesn't have to be surjective anymore, but it does have to have a dense range. All right, so we assume also that there's an invariance under some symmetry groups, so translation is really the main interest, and that this gives you a conserved quantity. So, I mean, we assume it gives you a conserved quantity, we'll call the momentum P, which is also smooth, or C2 at least, and when you're restricted to this open set in the well-posedness space, and it has to interact, the translation invariant, so translation has to interact nicely with J, and it's hard to explain what that means in the general case, but I'll do it in the specific one. So for our case, what is the symmetry group? It's just translation, so you just move everything to the right. There's a little bit of annoyance because these guys behave differently, right? Because the composition is okay, that's the headache specific to this problem. And it's easy to see that the energy and the momentum are conserved, or invariant to this translation. So what does it mean by nice interaction between J and T? Well, dt, let's call, it's not the derivative, but it's something related to it, is this kind of affine mapping. And it's an isometry on any of the spaces we're working with. It's unitary in an appropriate sense that I won't specify, and it commutes with J of U in the following sense. So you have this kind of identity where, so dt star, the adjoint to this, applied to J of U times I. This is not the identity, right? It's the association between X and X star, and commutes in this way. Okay, so I apologize, this is very difficult. That's not the identity either, right? That's capital I and then dt, right? But okay, so you have sort of nice behavior. Okay, so a traveling wave in this sort of abstract context, it just means that you have a solution of the equation which corresponds to translation with some speed c of a stationary solution, capital U. Stationary solution should be in this well-posed in this space naturally. And we assume in the abstract setting that we have a one-parameter family of these solutions and indexed by, say, C, and that they are both in well-posed in this space and also have to be very smooth, right? So this is natural, and that's C1. Okay, so inserting this ansatz back in the equation, we see that UC is a critical point of the augmented Hamiltonian in the usual way. And the point vortex problem we're going to use as our family, this S-slope, this curve of solutions that we constructed that I presented earlier. The only issue is that you don't really want to vary epsilon because that's in J, right? So the right thing to do is to vary A instead. And well, you don't want to vary A either because this whole theory, you want to vary C, right? So I'm just glossing over some details, but you fix epsilon and you can reparameterize the curve in terms of C instead of A, and let's just imagine we did that from the very beginning. It doesn't really matter. And so now our family is just eta depending on C, phi depending on C, and x bar depending on C. They're in O. They're also in the very well-Posedon space, and here C is very, very small. So everything is small. Okay? And we can show that this meets all the required hypotheses. So we have to assume now that the second variation, which extends to a bounded operator from x to x star, so this is on a smoother space, right? So you need to do a little more work there. Self-adjoint in an appropriate sense, and has the right spectral behavior that you would need for the Grillakis, Shatah, Strauss in the classical setting. I'm running short on time, so this is all what you hope. And then so what we're interested in is orbital stability. So what does that mean? I just introduced a little vocabulary. So you take any function and you just look at the translates of it with respect to the symmetry, and we call the U orbit generated by T. And our objective is to prove that that these are stable or unstable. Right? So that in mind, so fix some radius capital R positive, and we look at these tubular neighborhoods. So let's see. So capital R superscript W means I look at functions that are in the well-Posedon space, and I look at the closest translation I can get. I mean, the closest I ever get up to translation to a member of the family of traveling wave solutions. And I want that to be less than R. And likewise, if I have a superscript V, I'm doing the same thing, but I'm looking at functions that are in the very smooth space as well. Okay, so R is the radius. The superscript is just the regularity. Okay, so then the main result is as follows. So look at any non-zero wave speed, and suppose that you've built this, you've taken the moment of instability, and you know that it is convex at some C. Then you see is conditionally orbitally unstable, or sorry, orbitally stable in the following sense. And so we have to make a few provisos.
What D of C was?
D of C is you evaluate E of UC minus C P of UC. So you just take the augmented Hamiltonian along the curve of solutions. So this is the... Okay, so the statement is the follows. So for any capital R and lowercase r positive, there exists some smaller radius R naught, such that if you start off with initial data in the well-Posedon in a tubular neighborhood in W, of radius R naught of the curve of solutions, and you have a bound in this very smooth norm of capital R, then your solution remains in that tubular, in the larger tubular neighborhood for all times as long as it exists and obeys this bound, right? So it can grow in norm, but it can't. You need to have some uniform control on how far it grows in this higher energy norm. As long as you have that, then you can get the usual orbital stability statement. So if for whatever reason you can control this globally, then you're in very good shape, and this is a standard, a more standard non-conditional result. Okay, conversely, if you have that D is concave at some value of C, then you have conditional orbital instability, and so this is a bit more involved. So there are a number of different alternatives. So again, let's fix a capital R positive, sufficiently small, and one of three things has to happen. So either you have sort of a global ill-Posedonness, so there is some initial data that lies in this tubular neighborhood, and the well-Posedonness norm is well-behaved, and it lies in O, and there's some finite time for which these quantities blow up. So that means either it blows up in this well-Posedonness norm, or it's something like the point vortex hitting the surface, right? So something degenerating the problem. Another possibility is that you have some uncontrolled growth in the higher norm. So for all positive R, there exists some initial data that lies in a tubular neighborhood in both W and V, but it exits this larger tubular neighborhood in V in finite time. So it meanders away in this when I'm looking at the higher regularity norm. And then the other one is what you want to have is the definitive statement, which is that you have instability. So there is some time, some radius. So for any R not positive, you can find some initial data that is in the tubular neighborhood of that radius, but exits the larger neighborhood at this should be R naught, I guess. Oh, no, so this should be R in finite time. Okay. So this is the standard statement that you would hope for, but we have to allow for these other ones because we've weakened things so much. Okay, so my remaining time, I promise I don't want to go over. Let me just talk about what does this mean for the point vortex problem. Well, okay, so we put all this, put our work into this machinery, and you get the following. So for any c small enough, then you have conditional orbital stability in the sense of the first theorem that I stated. Okay. And so to do that, of course, you need to verify all of these myriad hypotheses that I put on the board very quickly. And also you need, in particular, you need to show that the d double prime is positive, right, at these values, for small values of c. Okay, so this is, so how do we go about doing this? Well, the idea is somehow, which is it goes back to Milke's work on capillary gravity waves, very much inspired by it. So we note that actually if you look at the energy, then you have phi occurring quadratically, so you can actually eliminate it pretty easily. And so just take, you can define this augmented potential, V aug c, where you just minimize the augmented Hamiltonian over phi. Right? So now it depends on just eta and x bar, and you can write down what that is explicitly. It has this kind of phi star, the minimizer has this expression. So it's just, so this is the inverse of the Dirichlet-Neumann operator, and then this is what you would see without vorticity. Now this is an additional term, but this is totally explicit, modulo knowing where x bar is. Okay, and then once you've done that, now you need to just, so this quantity basically is what you care about rather than EC, and it suffices, in fact, to compute the spectrum of this guy instead. So this is a very long argument. As I said, Milke kind of lays the groundwork for it, so we very closely followed that, but everything is much harder because the symplectic structure is really unpleasant. But anyway, once you do that and then do it several times so you actually get it correct, what you find is that indeed you do have the right spectral behavior that you want. So there's a negative eigenvalue, 0 of course from the translation invariance, and the rest of the spectrum is strictly positive. And then you also compute D. So you can do this explicitly again because we've got this very nice, it's just an implicit function theorem argument to generate the existence theory in the first place, so you know exactly what these waves look like to leading order. And so computing D double prime is actually relatively simple. Okay, so that's the proof of the theorem, and let me just end by saying that, okay, so we hope to be able to apply this sort of abstract theory to other problems because, as I said, there are I think a number of places where it could be helpful. So one thing which sort of comes out almost for free is that you can, so Bono, Suganius, and Strauss had a very nice paper where they prove stability or instability of KdV solitons, and they don't use the Grillakis, Shatah, Strauss. They get around the fact that dx is, that you have J equals dx by using another conserved quantity, which is the mass. So we can do it sort of directly through this framework now because we don't need to worry about the surjectivity of J. So it's not a new result, but it's a new proof. And then, okay, so many other problems hopefully in the future we'll be able to do. So internal waves, as I said, we have this nice formulation due to Benjamin. Vortex patches is something I'd be very interested in, and of course these sort of other dispersive model equations would be very nice to look at. Okay, so let me just stop there, and thank you for your attention.
Thank you very much. Is there any question or comments?
Yeah. Oh, go ahead.
Okay.
Someone else first.
Okay. So my question is, how important is capillarity in what you do?
For the existence theory, or for it doesn't really.
Stability.
Pretty important, I think.
So if you set it equal to 0, it will.
Yeah, the spectrum is going to change, right?
Okay.
Yeah.
But that's what you would expect.
Right.
So to continue that question, so you could have no surface tension in this. Is that what you're saying?
No, I'm saying that if we didn't compute without surface tension, but if you did, I think that the spectrum would be different, and you may not be able to apply the theorem anymore. But also the existence theory without surface tension isn't. I think we have some preliminary results, but it's not as well developed yet.
The existence theorem is what?
not as well developed yet. I mean, without surface tension. In fact, it's the problem without surface tension is, as far as we can see, you can't bifurcate from 0. You have to bifurcate from like fluid number equals 1. So a lot of these terms that we're treating as perturbative wouldn't necessarily be perturbative anymore.
Okay, then I had another question. This computation of this index of stability D.
Yes.
You just said you can do it, but that's crucial, of course.
Yeah, yeah.
And could you give us a little more hint about that? Is that a straightforward computation?
I mean, it's not a straightforward computation, but if you have this paper of Mielke, it's something you can understand with a lot of effort reading that paper.
You can't get it just in a simple.
No, it's not. You can't just stare at it. I mean, we did it.
Scaling.
Yeah, no.
That's sort of a formula.
It's very hard. But I mean, it's.
So you're omitting
I'm omitting
a lot more there.
quite a bit of. I mean, 6 months or more of work. Yeah, but I mean, it's not very. You take everything Mielke did, and then which is very long and very hard, and then you add, 10 pages worth of terms to it, and then you redo it. And we did it wrong actually several times, and finally we got the right answer. And
So you don't really compute D of C.
Oh yes, we do. Yeah, we compute it. We get its leading order terms and its derivatives. Yeah.
But that's for small c, right?
For small c, yeah, no idea when c is large.
Oh, so expanding in powers of C.
Powers inside of c. That's right.
So the spectrum could
Yeah.
a larger index of instability if
Or it could switch. I mean, that's actually something we'd love to see if people do numerical simulations and maybe the sign of C changes as you go larger. That's D of C, sorry, D to a prime of C, but we don't know.
So, for example, Lewandowski has done computations of some certain other cases where he the computations show that when C is small, you make one, or C is large, you get different situations. Yeah.
So there's potential for that, but I mean, I'm not a numerical analyst, unfortunately, so I haven't been able to. We'd love to have people do it, but we haven't done it ourselves.
I just have a question about the sense of what conditional actually means. It's not just a solution, it has to exist.
Yeah, it also has to stay bounded in this higher regularity.
So you need extra bounds. So if you blow up and if some 100th derivative blows up, then your theory doesn't apply. Right.
Right. That's an alternative that we have to allow for. I mean, probably not 100th. I mean, I think we can get down to like 3 halves. Whatever. I mean, yeah.
It's very small.
Yeah. No, I don't see a way out of that, unfortunately.
I have another question. Jiwoo Lin was telling me recently that he and some co-authors have also have similar kind of abstract theorem.
Yes, he is a very.
In fact, there's a rather long preprint.
Yeah.
How does that relate to your abstract theorem?
I hope to be able to tell you more about that soon.
What?
I hope to be able to tell you more about that soon. I'm still working through that work. It's quite momentous, I guess.
Maybe it's somehow, it must be somehow related.
But
I think
you
it's-
need to compute the second derivative d. That is also crucial in the.
Oh,
so
yeah.
the links the assumption that you still need the derivative, the second derivative d, the information to get some index the stability, instability for the two links.
Yeah, you still have to, you
Still
always
need
have to
that.
compute
Right.
the
Yeah.
second
So that
derivative.
is
No, I think
crucial.
that theirs is much more general. Like I think they need almost no assumptions on J at all. I mean, it's really quite nice.
You don't need a J, right? J is the. I mean,
Right, because
J is
people-
not supposed to be the subjective. It's not. That's not necessary.
Right. No.
Yeah, both theorems, you
Yeah,
said
yeah.
yours don't have to be subjective,
Right.
and also Jiwoo Lin's don't
No,
have to be
that's not
subjective either. I remember he told me that. But, okay, it's, you have to discuss it with those guys.
Yeah.
Yeah.
Look forward to that. Yeah.
Maybe the other.
So, thank you. I heard this lecture before, but one thing I don't understand with your sketch.
Yeah, it's bad, right? Should go the other way around, right? But
Yeah, but is that physically you would have an asymmetry because of the vortex? I don't see any asymmetry. You have that in your formulas, but I mean, you have an asymmetry in.
No, everything's even. I mean, the horizontal.
But okay, so if you do that in physics, if you try to like do an experiment, you would immediately have an asymmetry And it seems that you kind of disconnect from this asymmetry. That is the first thing, that's the main point of like your vortex.
Mm-hmm. Yeah, well, there's the phantom vortex in the air,
that
maybe.
is an object.
Yes, sure.
And you can play with this.
Mm-hmm.
It's the first thing you see in the lab.
Mm-hmm. Mm-hmm. Is it possible that the
But
phantom
it's-
vortex
so
is
it's
not,
like,
maybe that's not in the lab?
If you don't get this asymmetry, then it's kind of a different word. Because you don't have any asymmetry here.
No, everything is even, that's right.
Your point vortex is directly below,
On the crest.
below
line.
the crest.
Yeah, that's,
Or trough, I guess, but yeah.
it's very strange.
It's very natural in the steady water waves. I don't know, but I admit that, yeah, maybe in the lab experiments it's not usual. John? Yeah.
Just to be clear, the flow is irrotational except at a single point. Is that correct?
That's right, yeah.
So what do you see?
What do I see?
What do you see in the flow? You have an irrotational flow and
You mean the streamline pattern, or so near the point vortex? They're circular orbits.
circular orbits around.
Uh-huh. I think actually that's another way of interpreting what this.
Speeding up, getting faster, as velocity getting faster as you.
So I haven't done any numerics, so I can't really give much of intuition on that. We didn't look very carefully at the dependence on C for the.
So now let's thanks to the speaker again.